Hello, my name is Robert Smith and I'm with New River Community College. And today we're looking at the effect of a common ion on a solution. So we're asked to calculate the pH of acetic acid solution. And then we're also asked to calculate the pH of the acetic acid solution when there is the sodium acetate present in the solution. So the first one is fairly straightforward, and the second one is just a little more complex, and it involves a common ion of acetate. So if we look at either uh, reaction, we can look at CH3, COOH, that's acetic acid, and when it's a weak acid, and when it's in solution, it yields a proton plus the acetate ion. And similarly, sodium acetate will dissociate, except sodium acetate will completely dissociate. It's a salt, so it does not come into equilibrium. And it will yield a sodium ion plus the acetate ion as well. Did not give myself enough room there. That's fine, though. So we have two equations, and they have this acetate ion in common. So in the first case, we're not worried about sodium acetate. We're just going to work with acetic acid. So let's scroll down a little bit. And we can start with an ICE table, and that's what you would generally use. We're going to do this very qualitatively. So we're going to use the approximation method with the ICE table. The Ka of acetic acid is small enough that, and our concentrations are small enough that if you were not to use the approximation method, it would give you a result very close to the approximation method. So we're just going to do this qualitatively just to illustrate a point. So if we take this first, let's call this reaction 1 and this one reaction 2. So we take reaction 1 and we create an ICE table by it. So we'll just rewrite that here. And we have initial change in equilibrium. And at our initial state, we have 0.40 molar of acetic acid. And we'll put the unit up here so we don't have to include it for each term. And we would have 0 molar for both protons and acetate ions. And we don't know what the change is initially, so we're just going to give it a variable x. And similarly, as we lose acetic acid, we're going to gain the same amount of both protons and acetate ions. So at equilibrium, our equations would be 0.40 molar minus x molar, and x molar. Now the Ka of acetic acid is 1.8 times 10 to the minus 5. So we're going to set up K is equal to products over reactants. So we have 1.8 times 10 to the minus 5. In this case, it's the Ka because we're dealing with acetic acid that's being dissociated, is equal to the products, which would be x times x, so it's x squared at the top, over 0.40 minus x. Now, again, we already said at the start that we're going to use the approximation method. So that's approximately the same as x squared over 0.40. And if you multiply both sides by 0.4 and then take the square root, you'll find that x is equal to 2.7 times 10 to the minus 3, which is also equal to our proton concentration. So H plus. So to get our pH of this one, we just simply take the negative log of the proton concentration, which is 2.7 times 10 to the minus 3 molar, and we get a pH of 2.57. Pretty acidic. Now let's see what happens when we include our common ion. So the main thing that's going to happen if you include a common ion is that our sodium acetate from number 2, so this equation 2 up here, what's going to happen is we start off with 0.5 molar. Oh, that didn't come out right. There we go. 0.5 molar. And it's going to completely break up. So we'll end up with, that'll go to 0, and this will have 0.5 molar of sodium and 0.50 molar of acetate ion. So basically what we're going to do is we're going to set up the same ice problem as before, except the starting amount on our acetate ion will be 0.5 instead of 0. So again, we use CH3, COOH is in equilibrium with H plus CH. Let's just back that up just slightly. Okay. So CH3, COO minus. And then what we would do is we'd have our initial, our change, and our equilibrium. And our initial, again, would be 0.40 molar, dealing with molar here. And our initial for our protons is 0, but because of that sodium acetate dissociating, we now have an abundance of acetate ions. So we start off with 0.50 molar of acetate. So then when we're subtracting X and adding to our reactants and then adding X to our products, and perhaps we should use something different like Y or some other variable, but went ahead and used X. And then our 0.40 minus X on the acetic acid stays the same. We have X for our number of protons at equilibrium, but for our number of acetate ions, we have 0.50 plus X instead of just X. And again, we're going to use approximation. So our Ka again is 1.8 times 10 to the minus 5. And that's going to be set equal to X times, well, typically we would do 0.50 plus X all over 0.40 minus X. And if you look at that and use your approximation method, we're going to just put a little tilde over the top to say it's approximation. You end up with 0.50x over 0.40. And this is because we're saying that 0.40 minus X is very small compared to 0.40 and also very small compared to 0.50. So we're just saying that 0.40 minus X is roughly 0.40 and 0.50 plus X is roughly 0.5. And if you do this calculation out, you end up getting that X is equal to 1.4 0.4 times 10 to the minus 5 molar, which is also equal to our concentration of protons. So then to get the pH, we take the negative log of that value, 1.4 times 10 to the minus 5. And when you do that, you end up getting our pH is 4.84, which is really interesting. It actually, the pH became more basic. It went up. This is, note that our pH without the common ion was 2.57. With the common ion is 4.84. So the big thing to recognize in all of this is that this is the introduction to why buffers work. When you have a buffered solution, which is a weak acid and its conjugate, then you end up having a solution that is more stable in the pH range. You know, if we were to take this to typically having a pH of 7 and introduce, because it's in solution with water, and we introduced acetic acid to that water, then our pH drops to 2.57. But if we introduce acetic acid and a sodium acetate to that water solution, it still becomes acidic, but not by nearly as much. So consider that as we proceed forward in investigations into buffer solutions.